has been discussed this week. This is joint with Michael Hopkins. And the talk is about the cohomology of a field with coefficients in Z mod 2, or really the underlying differential graded algebra. So let's pick a field K. And the whole talk, it'll be characteristic not equal to 2. And we'll work with the étale topology. And we're thinking about the cohomology of spec K, or K, with Z mod 2 coefficients. And more specifically, this is the kernel over the image, the homology of a differential graded algebra that underlies this cohomology ring. And let's recall that that's the same as the continuous Galois cochains. So if Ks is a separable closure of K, this differential graded algebra is also for the continuous group cohomology. Some reasons to be interested in this. It records arithmetic information. You could phrase quadratic reciprocity in terms of the cohomology. It arises in abstractions to rational points, and it gives information about the structure of absolute Galois groups. And we'll give examples of the latter two. This, as a ring, this is computed. So let's get some elements of H1. So we have the Kummer map. So the short exact sequence taking Z to Z squared. We can apply cohomology to it. As you know, and produce the map from K star to K star squaring, then to H1 of spec K with coefficients in mu 2 or Z mod 2, and then to 0 by Hilbert 90. So we have a way of thinking of classes in K star as classes in H1. So I can write down what H1 is, and then think of elements in K as elements in H1. So what we'll build we're going to build for A, B, and C in K star that we'll think of as classes in H1. We're going to build a splitting variety. Build a splitting variety for the triple Massey product A, B, and C, which we'll also define. The Massey products are sensitive to the information in the differential graded algebra. that's lost when you take the cohomology. But we're going to give an example to define what a splitting variety is and give a method of proof for the theorem by building a splitting variety for a cup product. So we'll start with an example. Splitting variety for a double Massey product, which is the cup product. To do this, and also to define what a splitting variety is, let's give the answer. So the Brouwer-Severi variety let's define it. So we have it'll sit in affine 3 space for us. We could make it projective because the equation is going to be homogeneous. But so let's Brouwer-Severi variety. It's given by the equation ax squared plus by squared equals z squared, and with the origin removed, so sitting inside 3 space with coordinates x, y, z. And it's a splitting variety means that, what did I do? Yes. Great, thanks. And what splitting variety means is that this has a point. So this is defining XAB. So for a field extension K to F, the following two are equivalent. XAB has a point over F if and only if the cup product of A and B pulled back into H2 of spec F with Z mod 2 coefficients is 0. So more generally, a splitting variety for a collection of cohomology classes is a variety that has a point when those cohomology classes pulled back to the field contain 0. Sorry. The construction and justification, or the proof of that theorem, is that the cup product has a universal torsor associated to it. So let's let H be the mod 2 Heisenberg group. So we'll let H be the group of 3 by 3 matrices with coefficients in Z mod 2. And H maps to Z mod 2 cross Z mod 2 by A12 cross A23, and that's a homomorphism by matrix multiplication. And let's call that map Q for quotient. And the kernel is a Z mod 2 sitting in by 1 goes to 1, 0, 1. This extension is classified by the cup product of classes in H1 corresponding to those homomorphisms. So A12, it's a homomorphism from a group, and that's an element of H1 of the group with Z mod 2 coefficients. So it makes sense to say star is classified by the element A12 cup A23 in H2 of Z2 cross Z2 with coefficients in Z2, and this is sort of by matrix multiplication. So And that's just another way of saying that if whenever you had, so given any representative cycles really, but let's say A and B in H1 of G Z mod 2, then we get a map from G to the quotient. So G maps into here by A cross B, and there exists a lift to H. The fact that it's classified by this class is just another way of saying that this exists if and only if A cup B is 0 in H2 of G. And this is the same as saying that there's a torsor, an H torsor over G such that Q star of it, so A cup B is equal to 0 if and only if there exists an H torsor E over BG with Q star, where Q is this quotient map still, with Q star of E, the Z2 cross Z2 torsor associated to A cross B.
I'm sorry, where does A12 live?
Here, it's an element of H1 of this group with coefficients in that. So if we thought of the projection from the
projection.
Yeah, so it's the, I mean, the A12 was pulled back from that projection class. So what we need to do to construct a splitting variety is to construct an H torsor with controlled push forward such that all H torsors come from the H torsor that's going to be constructed. So we'll build an H torsor that gives the Brouwer-Savary equation. So we have H acting on A2 by inducing the representation given. So if we take all matrices such that A12 is 0, that's a Z mod 2 cross Z mod 2 with the two vertical interesting entries. So we take, there's a subgroup given by A12 equals 0, and we can induce up to H of the representation given by A13. And to be overly explicit and get the Brouwer-Savary equation, let's write down what that is. So we have, let's let E12 be this matrix, and we'll let E23 be this matrix. And just writing out what that says, E12 acts by switching some coordinates for A2. So let's let A2 be spec k adjoin xy. So this acts by switching x and y, and this one acts by sending x to minus x. Oops. X to x and y to minus y. So then inside A2, let's let S be the locus where the action is not free. So where H action is not free, and that's when x equals 0, y equals 0, or x equals y. So then it's a theorem that is due to at least Serre and Godot, and probably other people as well. And it's straightforward to prove, but for any finite group, so in particular H, so this is an old theorem. So for any finite group, if you have G acting on U freely, so an open subset of some AN freely, then U goes to U over G is an H torsor, and it's universal, or at least versal in the sense, so is, or a G torsor. And the map from K points of U divided by G to G torsors on spec K is surjective. So every torsor is pulled back from that. So by building a representation and taking a quotient, we could get a universal torsor, but we still need to control the push forward under Q. So to do that, so we want to control the push forward under Q. We'll pick another representation, but this time of Z2 cross Z2. So H acts on A1 cross A1 through Q. So this will have coordinate alpha, and this will have coordinate beta. So by, the non-trivial representation, so let's say E12 of alpha is minus alpha, E12 of beta is beta, E23 of alpha equals alpha, and E23 of beta equals minus beta. And it follows from that same, from this same theorem, that then if we take, so A2 minus S cross these representations minus the origin, and divide by H, that this is a torsor with controlled push forward, such that every torsor with controlled push forward comes from this torsor. So this is an H torsor with Q star as described, and it's universal or versal in the sense that any such torsor, so let's say, is a versal, as in universal without the uni. So then, since we've done all the work to write this out, let's compute it and see that we get the Breuer-Severi variety that we said we would. So we want to compute that. And to do that, we want to compute that last torsor we were talking about. And so that quotient is the same as taking the invariance under H and then passing to an open subset of x and y. They were the two coordinates on A2. And then alpha and beta, and it's going to be convenient to take the alpha and beta with their open stuff already taken out, but then remove the codimension S thing later. You can do it both ways. So we're computing that torsor, and to do that, we take the invariance under H of this, and this is the same as first taking the invariance under the Z mod 2 that's up there is in the kernel of that extension star, and then taking the invariance under H over Z mod 2. But that kernel we induced from the character that was multiplication by 1 on that kernel, so it acts by multiplication by -1 on x and y, and then on the A1s it factors through Q, so it doesn't, since it's the kernel of Q, this C2 leaves those fixed. So this is just the symmetric square of that representation that was induced. And then this H mod Z mod 2, that's the Z mod 2 associated to E12 cross the Z mod 2 associated to E23. And E12 over there, it switches x and y, and it takes alpha to minus alpha. So we can split these up into simultaneous eigenvectors for the action of these commuting matrices. And so what we get is that the things that are invariant are x squared minus y squared over alpha, because when you switch x and y and also multiply alpha by -1, that's fixed. And then xy, the E23 takes y to minus y, so we can correct that with a beta. So we get x over y over beta, and then x squared plus y squared is fixed by either switching x and y or multiplying y to minus y. So then what we get is alpha to the, or these three, alpha to the plus or minus 2, beta to the plus or minus 2. And if we call alpha squared A and beta squared B, and we call this coordinate x, this coordinate y, and this coordinate z, what we're getting is that this is the Breuer-Severi variety. So we have x, y, z, at least when you fix A and B. So then we have a x squared plus 4b y squared equals z squared, and that's the same as that Breuer-Severi. So that's the splitting variety for the cut product. The whole cohomology ring has a computation in terms of the field itself given by the Milnor conjecture. So the Milnor conjecture Blavatsky says that you can describe the cohomology ring as a tensor algebra of those classes that we had in H1. They can be cupped together, and if you cup them I times, you get some element in HI. So this piece is giving some sort of element of HI. And then the theorem is that the only relation is, well, besides 2 for 2 mod 2 coefficients, but then the only relation is coming from the Steinberg relation, which is that x cup 1 minus x vanishes, and which you could see from the Brouwer-Savary variety that we just did. So let's call this, so this combines stuff about the multiplicative properties of K with the additive properties of K. So
how does that kill the K star squared just in H1?
it's
Oh, that's
just,
great.
so we'll call this field arithmetic. Description of the cohomology. But as we've already said, this is the cohomology of differential graded algebra. And you can ask, is there a field arithmetic description of this differential graded algebra up to quasi-isomorphism? And folks didn't like that phrasing because field arithmetic is a little vague. So we changed it to, is this formal? In other words, is the description of this differential graded algebra just sort of the same as the formula up there? The differential graded algebra would just be quasi-isomorphic to the cohomology ring. But work of Pozyt-Selewski, excuse me? That it's this is quasi-isomorphic to the ring without the differential. Shows that it's not formal. So C star spec K Z mod 2 is not necessarily formal, which leaves open the question of what is that DGA. It has some description that includes more than just the underlying cohomology ring. And so we ask if there's a refinement of the Milnor conjecture that expresses the whole differential graded algebra.
Can you say what kind of K you have to take for this not to be?
For this not to be?
Like, which K is the counterexample?
I forget. I mean, there's a class of them.
Are there K where it's not equal?
No.
It's like number of fields, are there examples of number fields?
There are definitely examples of local fields. So if you were going to try to compute what sorts of differential graded algebras have a given cohomology, one of the first pieces of information that you'd wind up wanting to write down what the differential graded algebra is the triple Massey product. So let's define that.
Sorry, you know when Klopsowski's work was?
It was an archive post on like Thursday. No, but I'd been in touch with him before. I mean, triple Massey products. So we're going to give a definition and a quick definition. So they're partially defined and multi-valued. And they're defined, so we'll do things in H1 because that's where the splitting variety is. So if you had 3 classes in H1, the Massey product is defined when A cup B is 0 and B cup C is 0. And then in this case, so when defined, there are classes, cochains. There's an EAB in C1 such that the boundary was this cup product, and EBC in C1 such that the boundary is B cup C. And then you can form, the triple Massey product is the set of all combinations built like EAB cup C plus A cup EBC for all choices of those cochains as above. And that's the same as choosing a single one, just choosing your favorite, and then taking all the translates of it by the ideal generated by A and C, because if you take different choices, for this one, say you're adding something with 0 boundary, cup C, and that's then in the ideal generated by C. Okay, so a classic use application of these is they distinguish, so H star of the complements. So we have the complements of 3 unlinked circles and the complements of 3 circles that are linked like the Borromean rings have an isomorphism on their cohomology, but they can be proven to be non-homeomorphic or homotopy equivalent by using these Massey products. So the Massey products on the left are trivial, so triple Massey products are trivial on the left and not on the right. Okay. So here's the splitting variety, and it's It generalizes it's a generalization of the equation for the Brouwer-Savary variety, and here's the equation. So define x, a, b, c inside GM cross. So this is going to be the splitting variety for the triple Massey product associated to the classes in H1 given by A, B, and C. And if the coordinates here are y1 through y4 or y underline, it's going to have a point when it's defined and when and 0, yes. So when an obstruction vanished, like if a Massey product came up as an obstruction. So,
So you're saying it's going to be defined even if the cut products are not 0?
well, I mean, this is going to be defined. It's going to be an equation period, and it'll have a point when the Massey product is defined and contains 0. And so this. The coordinate here is x. So the Brouwer-Savary equation over there, you would have that if you look at x and z, you'd have that by squared was a norm of a certain extension. And the equation cutting out x is that b x squared is the norm of the extension you'd get by taking square root of a, square root of c over k and applying it to y. And then just to be clear about what happens when a is equal to c, what is really meant by this expression, as you can probably guess, is that so if we take the product of y1 plus minus 1 to the I square root of a y2 plus minus 1 to the j square root of c y3 plus minus 1 to the I plus j square root of ac y4. And then this can be expanded just in terms of a's and b's. I mean, a's and c's. So this is just an entirely elementary definition of a variety. So the theorem is that, so for k characteristic not 2, a field, and k f, a field extension, then x, a, b, c, f has a point if and only if a, b, c is defined and contains 0. In H2, spec f z mod 2. So since this is only one equation, if you set things up, you can get many equations and many variables. Since these are versal torsors, they're not unique in a certain way. There's flexibility in what you'll get. So the result here is that you can deal with indeterminacy, you can control the push forward, and that you get an understandable answer that you can then work with. So let's use this to study let's say the Galois group, and then also integral points and an automatic realization. So here are some applications. The first one was already known, but you can see it from here again. So the Massey product of ABA contains 0 whenever it's defined. And that's because the norm, so you can just close your eyes. So when A is equal to C, you're technically looking for a solution to that equation, which is degree 4 on one side and degree 2 on the other. But you can actually just find something whose norm for that extension satisfies it, and that will also produce a point. So because if you just put A equals C, you recover exactly, if you interpreted that norm literally as the norm from K adjoins square root of A to K, that is the Brouwer-Savary variety. So then it's immediate that that's true. And that also follows from formal properties of Massey products. So this is already known. Leap and Wadsworth wrote a series of papers doing a Hasse principle mod squares. And for the biquadratic extension given by K adjoins square root of A and square root of C, that's the same as the Hasse principle for that variety XABC. So they proved, let's say it's a Hasse theorem, and it's also the title of the paper. So for this theorem, for the extension, K adjoins square root of A, square root of C, is equivalent to XABC satisfying the Hasse principle. So it does, and it's also straightforward to see that Massey products vanish for global fields. So it's a calculation that ABC vanishes, meaning whenever it's defined, it contains 0. So that implies that for global fields, characteristic not 2, the Massey product, the triple Massey products, all vanish. But you can do better than that, and Jan Minach and Nguyen Dai Tan and independently Suresh Venapalli saw that this variety actually has a specific rational point, meaning that all fields have their triple Massey products vanishing when they're defined. So X, A, B, C just has a rational point that you can write down. So we get that ABC vanishes whenever it is defined. And that means that the following is true for fields. Namely, if you start out with a Z2 cross Z2 cross Z2 extension of a field, you automatically get a certain other kind of extension above it. So let T.
What do you mean that a posteriori at your second point to be the splitting variety?
Yeah, I mean, for you won't get then that the integral. So we're going to make another application in a second, which is that this. So Massey products come up now. Actually, let me just get to it in a second. Also, I mean, this is the way you proved that. So okay. Except Jan Minach and Daitan have independent related results that do cool things. Well, let's write down the consequence. This can be phrased in terms of sort of elementary Galois theory, and let's do that. So if we let T4 in GL4 C mod 2 be the group 1, 2. Then given a Z2 cross Z2 cross Z2 extension of K, which is going to be, there's automatically an extension extending that, say T4 extension L, extending that. Sorry, yeah, with okay. Furthermore.
Is that the same as saying that if you have an extension of T4 mod, the final limit to the end, then you have another T mod?
It's the same as saying that when you take that mod out, that extension's classified by the Massey product. So that classification of that extension is in an old paper of Dwyer's. Yes?
You want it to only if the empty triple part.
Well, but that's what the number 3 was for that. So this is still over a field. And let's think about rings. So Massey products come up when you're doing lower central series or unipotent obstructions to rational or integral points, like Min-Yang Kim comes up with some explicit Massey products in that way. And I did too in another context. But here, just by construction, they succeed in showing that this variety has no integral points over appropriate rings. So let's write down an example where this Massey product successfully shows you have no R points. So this is thanks to calculations of Johann Gartner. So if you let R be Z 1 over 313 1 over 457, 1 over 521, and 1/2, and view those same equations, which are still defined. So then x of 313, 457, 521 has no R points. So I'd also just like to mention that Bert Guillou and Romiar Sharifi have nice results on arithmetic Massey products, and I'll stop there.